Alright, let's take a look at this problem. LRU cache. Design a data structure that allows the constraints of a least recently used cache. Implement LRU cache class. So here, initialize the LRU cache with positive size capacity. So we have capacity positive. And here we have a get function which takes a key here, integer, and returns an integer. Return the value of key that if the key exists, otherwise return -1. So okay, we return -1. So here if exists, return key. And put we have a key, we have a value, we update the value key if it exists. Okay, and if exists, update, and here if not exist, add. If the number of keys exceeds the capacity from the operation, evict the least recently used. Get must meet of 1 average time complexity. Alright, so I guess so what's the capacity? At most 2 times 10 to the power of 5. Key values are around that. Well, we have this cache. We get item. Every key was 2. X key 2. So do we only have what's the size of this cache? So LRU key was evicted. LRU key was 2. LRU key 2. Cache is 1. We get 2. So okay, we put 4. Alright. Okay. Okay, so this is the capacity. Alright, so how can we do this? Let's see. If I have a queue, if I have a queue, alright, let's see. I have a queue, I put 1 there. I put 2 there. I get 1 there. I get 1 here. Push it there. Also put it here at the end because it is used. So for least LRU use Q to determine, Yeah, like determine. Okay, to determine which is out now. Right. We have two here. I missed that actually. So again, inputs. So I guess I need something like refresh, like yeah, def refresh use, and I will give the key, which is int. I won't return anything. I will just refresh it. Right. So here I'll have myself queue like that. Maybe I can use deck. Was it deck? Okay, I think it was deck. So I can use this DQ deck for Q. So right. So I'll use that now when I replace it. So I'll also have a hash table to immediately access it, right? So when I remove this from this queue, right, I want to put 3. I check the length of queue. It is so first thing is that, so when I get it, so here it not exists. If it does not exist, then so here I should do like, if do not exist, I need to add it, right? And I also have to shift like pop left deck, right? So I just pop left and then append key, right? And if it exists, then we just update it. Just update and refresh here. Okay. So, right. So when I update it, and like I put it here, I pop left, I append 3 here, and then let's see, here I have 3, and I get 2, it's not there, I just return that, and then for 4, I just pop this, and I have 4. And by the way, when I'm popping it, I should also here change the deck, not deck, but like the dictionary. So this will just take off one time. This will also take off one time. Refreshing means that we just have to take it from actually refreshing should, if it exists, So the refresh, if it exists and we get it, the refresh should be the bottleneck here because we want all of one. How do we refresh that? Maybe we also in queue we hold. No, we hold the locations. No, we cannot have that. If we have some kind of pointer, no, we cannot have that. If we have, okay, so I'm not sure. So when we refresh, we kind of have to. I guess this should not. All right. I'll start implementing, but it is actually a bit weird. So I want O of 1, but it says average time complexity, right? Not every time you'll always ask different one. If you always ask like something from middle, then it will. Okay, I'm not sure, but I'll run a for loop. If every time it exists, then I guess we will need O of n. But it's better than nothing, so I'm just gonna implement that. So for now, so for deck, I'll have that. I'll have dictionary, which will be my cache. So like this. By the way, this should be like this. I'll have that here. So if key is in self cache, okay, then we of course have to get it and also refresh it. So refresh use, I'll pass the key, and also I want to return the self cache key. So like that. Okay, like that. And here, so if self cache, if key is not in cache, then we just want to self that queue that pop left, and we'll get a key from here, remove key. So, and then in self cache, we have this remove key, delete it, we don't want that anymore. And I also want to Wait. So, okay, there's two cases. If it is not in the cache, then we check if self deck length capacity okay. So if the queue capacity is less than self capacity, then it is fine. And also else, if it is not, then I want to remove these. If it is okay, I can just self queue append key, and here also I can just cache add this value, and that is fine to do so. And if we don't have that, we just pop left and remove it in the cache, and then I want to append the current key to queue and do that. So basically this is like that if it is greater than or equal to capacity, we pop it, else we continue like that, and then here else, if it exists, then we don't have to consider this because we just have to refresh it, and for that we just change the self cache key to the new value, and also we want to refresh it. We want to use refresh use key, and so this is my algorithm like this here. And here in this I basically go over and then pop that. Okay. Okay, I'm just gonna be back in a minute. Alright, I'm back. So, okay, I'll be continuing implementing this. So here, what I'm going to do is going to find the cache. I mean, this won't be of one time complexity, but maybe if we, I mean, if I, instead of queue, like if I use ordered dictionary, or like a double linked list, instead of queue, if I use linked list, but is it easier to find if I use array, normal array, then it would be login time. Okay, here instead of for loop I could use login binary search, but it's not sorted, so I cannot do that too. If I use LRU, ordered dictionary, then yeah, that's also possible, something possible, because otherwise it's really hard to do this, to be honest. So from collections, if I have ordered dictionary, so instead of that, if I have ordered dict, I have this capacity, and if I use this capacity later on, so I don't need the refresher now. So I check if it is in the cache. I just return it. Okay, just get it and return it. Maybe here I just remove it first. Self.cache dot. So what was it? Ordered dictionary in Python. What were the functions? I think. Okay. Let's see. Okay, let's click this. So I have move to end, last true. I have pop item, and okay, I can use this. So I can move to end key, right? This is the key. I move to end, I add this, I have -1 there. If that's the case, if it is not in the cache, I don't have to do this. I don't have to append here. I just have to cache it like that. But after this, if how do I remove the first item? Oh, actually, it is just here. Pop item last. Okay. So I just self cache that pop item like that, right? I just pop that item if length of self cache is greater than self that capacity. If length is now greater than self capacity, I just pop it, and else we just, if it is not in, we just add, but we update it. So here we do the same operation like that. We put it in the end like that. And okay, I think this should work, but where is this from? Collections, ordered deck. I guess I need ordered deck. Where is it? Like that. Alright, let's see. So if key is in cache, we move key to end. If we return the key, and here we don't have that key in cache, we put it in, and then we check. So let's see. All right, I have 1. Yeah, I put it. So this is 1. This is 2. Then I change the order. Where is that? So it should be here. Okay, I have 1, 2, and then later in the third time we call this this item should be last true. Actually, this should be false. We pop the first item. Okay. So let's see. Let's submit this. I mean, I don't have any other test cases. Let's see if this works. All right, it works. So what's the complexity here? Of course, O of 1 in this and O of 1 in this. And this is, of course, the capacity is O of C. The size is O of C. So that will be my solution. So I cannot use queues because it's hard to refresh the queue. I could maybe use link this, but again, it's pretty hard to do that. I probably have to see how this is working. Where is that? So I have order entries were added. So it returns a dict and how it keeps. I'll probably take a look at that. So here, yes, it is. This is how it is implemented. But I will take a look at that. So we'll see it. Yes. All right. So okay. So that's it. So can I run this without prints? All right. Cool. So that's my answer to this problem. It's pretty hard to actually. Let's look at the solutions. Oh, this is premium, so I cannot show it on video. But okay, let's take a look at this one. Like, yeah, this one is also fine. So here there's a way to do it, like with head tail. You kind of have to. It's really hard to go over it, I guess. Head tail, you have to create the node class and so on. There is the shorter version. I'm actually curious, how do you find it and search it? And just remove. Hmm. When you remove, well, I guess in dictionary you're holding the key. Yeah, I'll actually, I'm just gonna look at it and then explain. So if you take a look at this, I checked the actual implementation of ordered dictionary. It is actually using dictionary and double linked list. It is similar to this solution here, but it is different in its built-in library. But the idea is simple. Here in a node, we have key and value. So this is like acting like our key value pair in a dictionary, and we have pointers to previous and next node, and we have a capacity here, and we are also having a dictionary here. We create the dummy nodes in head and tail, and then head next is tail, tail next, tail previous is head. So this is basically the setup we have, and here when we get it, we check the dictionary. If it is in the dictionary, we put the value into n, and we remove n, and then we add n back, and we return that value. If it is not in it, then we just return -1. So if we just take a look at this remove, we will see that the previous node, so we pass, by the way, we are passing the node there, here, passing node, so as a value, we are, so maybe it's better to look at this one first. So, okay, where is it? So, okay, okay, here, set. So when if it is in, we remove it, but if it is not in, where is it? Where is add? Okay, it's kind of hard to find it. So we create a key value pair like this. If it is not in the dictionary, if it is in the dictionary, we just remove it and then create a new one. To make it simpler, so we just remove it and just skip this one for now. So we create a node and then we add that into the linked list. And how do we add it? We put it here like this. So the current, like P is the tail's previous one, and then P next will be our current node, and node, so the tail will also point to node. So we are adding it just before the tail and before the previous element before tail. And here also we have to change the next and preview of the current node. So we just insert it just before the tail, and when we're removing it, we're simply passing the value like this, and then we are getting the previous and the next one, and then from previous one we connect it with the next one, and from the next one we connect it with the previous one. And here in the set, of course, when we continue, we put this n into our dictionary. So we will have a dictionary of nodes. It's like I'm sorry. So in nodes, for keys we have nodes. For every key value pair we have the key, and for value we have a node. And using that and double linked list structure, it is all of one time to remove and add. And as you see here, where is it? Okay, where is that? So here when we remove, when we add, so my only, okay, when we are adding, we are always adding before the tail, but when we are removing, since we have access to the node, we connect the next node and the previous node together, and we are done with we just removed the in between, what we are looking for. And here, of course, we have a capacity, and the capacity is the length of dictionary. If it is greater than our dictionary, then we basically put the next head into n. We just remove that one, because that the leftmost one closer to head will be the least used one. So we just remove that and delete the dictionary key here, as you see. So this is simply the implementation of ordered dictionary in Python with double linked list and hash table dictionary. So all right, that was it. I just wanted to go over this. I also checked the solution, but this is much better. The solution I went over it is much simpler. So this is a good way of doing that, but knowing how to implement LRU cache with double linked list and dictionary is also helpful. I will probably upload one more video doing that. So yeah, that's it. So for now, it is the optimum way of implementing it, but this is the high level code using a dictionary. So okay, so that was it.